Okay. So we'll talk a bit about who Jenneke Johansson is, some of these common flow problems, ways to overcome flow issues. We'll talk about what this really means, and we'll go through this Ravensthorpe case study. So again, Jenneke Johansson, we're a very specialized engineering firm focused on helping our clients handle bulk material through their process. So they know what they want to make, but actually getting it through their process is often what holds back the plant and causes people to use a lot of hammers. So we've been in business for over 55 years. So Dr. Jenneke came over from Poland during World War II and wanted to make a difference in a field of research. And he found that nothing had really been done in the field of bulk solids handling. It was just a black box. You create a hopper, 30-degree hopper, 60-degree hopper, and then hopefully it works. And if not, you just bang the heck out of it. And he found that really no science had been applied to that. So he went to the University of Utah in the 50s and 60s, developed this whole theory of solids flow, kind of the equivalent of like Bernoulli's equation for liquids. He developed the equations for powders, dirt. And so that's a science that's still used today. We have offices all over the world: Australia, Brazil, Chile, Canada, an office in Houston, and our headquarters is in Massachusetts. Pop quiz. Which office did I open up? Australia. I did open up the Australia office. Ding, ding, ding. So open that up. It's about 10 years ago. I was there for 3 years with the family and got up and running. It's still going well. Lots of mining in Australia, to say the least. So everything from on-site inspections, maybe there's something currently going wrong with our clients' plants. So we figure out, kind of like the doctors, I call in the doctor, figure out what's going on. We run some tests to make some diagnosis of the problem, come up with recommendations to solve those problems. And then we can go further into computer simulations, which we'll talk about, discrete element method modeling. Anyone heard of DEM? Some of you guys have talked about in your class. Rob Reeves says you had. So Rob and I worked together for many, many years because Hazen and Jenneke work hand in hand because our tests are different in ways to characterize the material. So again, all industries, things you wouldn't even think about. Now, we have a chain. Does that look like a strong link? Not very strong, right? So often we find that bulk solids handling is actually the weakest link of the chain. It's not the glorified part of your process, but yet that is probably the part of the process that will give you the most headaches. So as you find the ore, you drill it, you blast it, you have nice big pieces of rock over there, easy to handle. As you reduce it in particle size, and can become more difficult to handle, especially based off moisture content, particle size, distribution. But at every step, blasting it to screening it, crushing it, you're adding value to that ore, right? Because once in the ground, can't add value to anybody. You dig it out, you reduce the particle size, you're adding value. Does that make sense? And that's what you guys are figuring out, right? But what happens if your material doesn't flow through that system? Then you don't get to add the value as fast as you want. You don't get to make as much money as you want to make. So this is a very familiar scene to our clients. I love this one because it's very true. So you got the guy trying to bang on the side of the hopper. I'm going to show you some brilliant hopper photos, all dented in. There's the guy trying to dig it out, rot it, and here's the manager. What's he jumping up and down about? This is costing time, right? Time is money, especially for mine, right? The throughput, it's all about throughput. And taking very unsafe actions to make this work, to try and get it to work. So a phrase we say, it's not rocket science. And it says, it's time we face reality, my friends. We're not exactly rocket scientists. Look at this, they're rockets. But we actually say it's more complicated because the material you're trying to handle can change throughout the process. It can change if the moisture contents change. It can change if you change the particle size. The way it flows changes. So that's what makes it difficult to design for. Now, when you're going into your projects, your ability to influence your design is the greatest at the beginning, right? There's no steel on the ground. So however you design your whole handling process, you have a great ability to influence it. The cost of making the change is very, very low, as you see in the blue line. So as you move from the study phase to the execution phase on the x-axis during your project timeline, you can see that cost starts to increase, especially once you freeze that scope. It starts to become more expensive to make changes, and you start cutting steel, very expensive to make changes. Your ability to make positive changes decreases. But look at the red line, the impact of a bad design. You don't see it, right? You don't see it till you come through the execution phase and you start up. And then what happens when the material doesn't flow through? It doesn't feel very good. It's a challenge. And unless you've lived through that, you as a fresh engineer, be like, can't be that hard. I'm fine. I sleep really well at night. So, but if you've gone through the ringer and it doesn't work, it's a challenge. So how do we get this right? Well, there's been some studies done. One was a McNulty startup curves, and McNulty studied, and you looked at, okay, depending on what they were building and how new of a design it was, how successful were they likely to be during startup? So if you had a very mature technology, standard equipment, very thorough testing, that's your best potential result. Because as you go through your commissioning period, you know, around 12 months, you're getting up to where you want to be productive. However, if you have a first of a kind process, maybe you had insufficient front-end loading design done, then you see your chance of success decreasing. If you have limited testing, maybe a project is fast-tracked. Guarantee you at some time in your career, you will be on a project that will be fast-tracked, and you will not have enough time to do all your studies. The likelihood of success decreases significantly. And then if there's limited testing, poor feedstock characterization, we see that goes even lower. And if it's a very complex flow sheet, it's a very new process. Look at this, even after 3 years, they found that there were only about 50% of design. Yes, question.
So you said it was interaction. You know who Carrie is?
I do not know him personally.
All right. He went to California.
Okay.
At USC, but he got his master's at Marsden. PhD in Colorado State Mines. I just saw him last week.
No kidding. Well, there you go. His curves are living. Is he really?
Yeah,
Oh, I like it.
That's where you.
For those online, I'm repeating this, that I've now found out Terry McNulty is very famous in these regions.
He went to school in undergrad, USC Chemical Engineering.
Okay, USC Chemical Engineering undergrad, and then Colorado School of Mines.
No, Montana Tech.
Oh, Montana Tech.
PhD.
PhD, Colorado School of Mines. Man,
National Academy in.
that is smart. That's awesome. Good guy. Love that.
All right, I'll put it in.
No, you are welcome to interact all you want. So I'm just setting the framework here, right? Why this is really important. Because liquids are fairly easy to handle. There's no internal friction. You can't form a pile. If you form a pile of water that's not frozen, let us know. You get some bonus points, extra credit. It's not sensitive to pressure. It's incompressible. So the flow behavior is based off the viscosity of the material, which is based off temperature, and you can look up that data. But bulk solids, we have this internal friction components. That's why you can form a pile. It's sensitive to pressure. The cohesive strength and the flowability of it can change based off that compressibility, that pressure. So then we need to run tests for flow behavior. I'm going to see if this works or not. If we get any sound, it may not work. Oh, okay. I'm going to be the narration of this. So this is Family Guy. And he's like, I got all this money and I already know what to do with it. Oh, you can't even see it. That's so sad. Well, you guys have seen Family Guy, right? It's so funny. You should have seen this.
Okay.
So he gets all this money and he's like, I want to buy a pool full of gold coins and dive into the pool.
Sorry.
You could play it, yeah.
Yes.
I just have to share what's the screen sharing. But anyways, he's like, I'm gonna buy all this. And I'm, Scrooge McDuck. I know, you guys are young. But he would always dive into these pool of coins and like swim as if he's swimming in water, right? So Family Guy's like, well, I'm gonna buy all these gold coins. And then he goes to jump in the gold coins. He's like, ah, it's a hard solid mass, not a liquid. Oh, that's the other, hold on, that's a different one.
That's a different one.
Yeah.
Wow.
We're just watching Family Guy for the rest of the day. Okay, hold on, let me pull it back up from. Sorry, I know it doesn't normally. Okay.
We're not gonna go crazy spending our winnings, and we're not gonna let this money change us.
What are you talking about? This money is our ticket to the good life, starting now. I just bought a giant room full of gold coins, and I'm gonna dive into it like Scrooge McDuck. It's not a liquid. It's a great many pieces of solid matter that form a hard floor-like surface. Ah!
Very specific.
Just share back your screen again.
Okay. Oh.
The whole day plan.
So anyways, oh, here.
Select this one, right?
Oh, yes, thank you.
And no.
So, but unfortunately, and you guys actually have an advantage because you do hear about bulk solids handling much more in your curriculum. Thank you, professors, for bringing that into the curriculum. But I was never taught about bulk solids handling. I had maybe one session on the Moore circle about soil strength. And so Jenny Q is actually a structural engineer who took some ideas from soil strength tests and adapted that for bulk solids flow. So a lot of times we get these problems in plants that we call are baked into the plant design. It's already been built. These problems are just there. Operators have somehow figured out how to try and keep material moving through the process, baked in. So a lot of the causes for that is just the flow material properties were not tested to be informed in the design basis. Maybe they borrowed values from a library. So I'll just borrow those values, use it for this project, not a problem. Maybe it wasn't representative samples. I know it's challenging in a new mine. Sometimes you only have core samples and you do what you can and do the best there. But a lot of times there's just a lack of awareness. Fast tracking a project, copying and pasting a design. Try not to fall in this. You're trying to do these front end studies. And then you're like, I don't know what it's really going to look like. Let's copy and paste another design. And then you get through their pre-feasibility study and nobody actually goes back to look at why that design was initially selected. Doesn't mean it was the right design for that project. It just kind of like was a placeholder and then never looked at again. So common flow problems we see are block transfer chutes. We see segregation issues. So this is a DEM run of basically the model that you have here. So you may have a nice blend of material and simply by discharging it into a pile, any kind of stockpile, you're going to have your fines separated from your coarse particles. So you can see that how the fines now are all in the center and the coarse are all on the outside. Now, depending on how you draw out of that pile, you may get a lot of fine material followed by a lot of coarse material, and that could have an effect of how material flows. Transfer chutes. Do you guys ever get in the design of transfer chutes? Or passes, absolutely. Building plug up, spillage, dust generation. I did not change the coloring in that photo. I took that in Australia, that aluminum and just the lighting of the green, and then all the dust in the air. And I was like, that doesn't look good or safe for anybody to breathe. Wear. So if your chute's not plugging, means materials moving through it, but then also means that the liners can wear out. In Australia, they would have these ceramic liners that were about 4 inches thick. Very expensive. Alumina ceramic liners are very wear resistant. They would sometimes burn through those in 12 weeks. 4 inches in 12 weeks. That's very high. That's expensive and they have to shut down, but they're also putting through 12,000 to 15,000 tons per hour in these export terminals. 12,000 tons per hour. It's phenomenal. So we do use DEM. We apply that to chute design, but with DEM, garbage in, garbage out. You can put any parameters you want in there. You can make any pretty picture you want, but what's most important is that that pretty picture matches reality. So using the test data that we're going to talk about can be inputs for that DEM design. So responds how we would expect the material to respond. Rat holes. So yeah, do you see this guy standing here? He has an air lance. So when a big stockpile is drawing material down and they're saying, hey, we need more material, go use this air lance to break up the material. If he's successful, what happens to him? He's gone, he dies, right? Dying, yeah, question.
Why do they call that?
Rat holes, good question. I think because it looks like a little rat ate its way down. It makes a hole. A little ratone. I was in Mexico and that's how they explained it. I thought, fair enough. Sometimes it's called piping. That's a really old name for that. So Jenneke in his work, Bulletin 123 that he published would say piping. We used to call it a rat hole. And then other times, here's a rat hole here, and they say we need more materials. So they send in the front, the excavator, and they push material into that hole. Now, what happens if all of a sudden this breaks through? He goes in with the excavator, right? It's going to fit into that hole. And unfortunately, people still die every year from that happening. This is not some fantasy thing. This is literally like they're trying to get the material through. So there's this, oftentimes you look at a stockpile design and it has nice big open flow channels and everything looks beautiful. But then you start up the plant and then all of a sudden you have these two steep rat holes, very limited life capacity. What changed? Maybe the particle size, maybe the moisture content, maybe the clay content you had in the sample. We look at caking, and not the good kind of cake like chocolate cake, vanilla cake. This is where powders stick together. Anyone ever have, you guys are kind of dry air up here, but salt caking together or sugar caking, right? That's because moisture has come in and caused crystal or liquid bridges to form between particles. Those dry out, become crystalline bridges, and now you have a caked particle. They can get very, very, very hard. So in a bin, you can have arching material or bridging material just doesn't come out. You can have rat holing. So there's some nice rat holes. And rat holes, it's not just like a pipe going straight down. Very misleading. It can actually like do a lot of funky designs all the way down. Anyone seen some crazy rat holes? So sometimes, see this picture here? It's a little bit small, but I was in Australia and when you walk around a plant and you see a lot of bin rash, something probably is going on there. Yeah, so it's like a rash on your skin, but something's indicating something's wrong. So there's a bin rash. So these guys in Australia put a sign that says, do not hammer. Problem solved. Because what was happening is this was on load cells. So every time you hit the side of that chute, it messed up their readings. Do not hammer. But they probably still had flow issues, even though they put the sign up. And I walked by the engineer, I'm like, do you guys have issues there? No, I think it works pretty well. It's like, I don't know if I can agree with that. Biomass is a big thing coming up, right? I know it's not necessarily mining oriented, but it will come to play because if you start looking at plants and they're using alternative fuel for power generation, biomass is very different. So biomass, very compressible, it has this interlocking effect. And so it may flow at the very low pressures, and then at medium pressures, it can bridge or arch. You might find some kind of happy medium where it will flow, but I mean, it can arch over a 20-foot cylinder of a bin. I mean, it's amazing how strong biomass can be. And part of it has a very low bulk density compared to all the ores that you guys look at. So as you scale it up, you don't have a lot of force of the material trying to force that bridge to break. So here's the sifting segregation I talked about. This can really lead to off-spec product. So in a very practical aspect, think of your Gatorade powder. You want the same color Gatorade and sweetness with every time you add the powder, or maybe a Via blends, coffee, like you want it to taste the same every single time. But if that's segregation, you may get something that's too sugary and not sweet enough. Maybe it's not the right coloring, and you get that inconsistent blend, and they don't want to sell you that type of product. Segregation over time as material flows through. You can get material to segregate. This is a cheese powder showing up in the top left, top right. So think of like your powdered cheese mix. You want it to be the right cheese, right? We all love our mac and cheese. My children do. Fluidization segregation. So this model is showing side to side sifting segregation, difference of particle sizes. Fluidization segregation is more where you have this air interaction of the particles, where the coarse go to the bottom and the fines rise to the top. That's quite common more in like a pharmaceutical application. Some powder material. There's dusting segregation. When you fill up some type of bin, filling up trucks, you'll see a bunch of dust and that's going to accumulate and settle around the edges. So flowability, I keep talking about this thing called flowability. What does that mean? This material flows. You hope it flows. Well, it really is, when we talk about flowability, it's a function of the material itself as well as the equipment you put it into. So you can have equipment that, or material that seems very difficult to handle, but you put it in the correct equipment, you handle it the correct way, and you're like, yeah, works really well. You can have material that seems very easy to handle, so not much thought is put into the equipment. You put in the absolutely wrong piece of equipment, and it doesn't flow well. Okay, so we had a client one time, and about 18 years ago, we did this big design, very fine powder, very difficult to handle. So we used this air-assisted discharge. Anyways, this very unique design to handle this powder. As a result, we just went back to site recently and they're like, yeah, it's worked from day one. Like it just works. And I was talking to one of the younger engineers. He's like, yeah, I think we just have easy material to handle. It just kind of works. We don't have any issues. I said, well, that's not true because here's actually one of the more difficult ones, but you have the correct equipment for it. So it appears to be easy to handle. So in our models, the default flow pattern through any kind of bin or silo would be funnel flow. You guys familiar with the term funnel flow? Raise your hand. This is your exercise component of the night. No, okay, some of you are. So in funnel flow, whenever you discharge, material is going through the center, it's funneling in on itself, it's stagnant on the outside. And then, sorry, it's hard to do this when I'm holding it. But you can actually get material to stay like a rat hole. There's a good demonstration. Well done right there. He's got his rat hole. You got a rat hole. Congratulations. We inject tiny rats inside of these and they create the hole. Just kidding. There's no tiny rats in your thing. But sometimes you got to tap it a little bit. So it's funneling in on itself and then it's done. Right? This doesn't seem very hard to handle, does it? It's not like it's not bad. But then here comes the sledgehammer. Yeah, it's stuck again. Here comes the sledgehammer again. It's just not a very reliable flow. Okay. So in that stagnant area, that is where material can cake and gain strength over time. It can degrade over time. If it's, for example, flour one time led to some salmonella poisoning in the end product, the baked good, and they traced it all the way back to stagnant flour in the silos. Bulk material handling problem caused people to be sick. We don't want that to happen. You also have limited live capacity because you're really not using the material along the outside edges. You also have varying bulk density. And these small little models, when this rat hole breaks, is there a structural issue? Is the world ending? Is it hitting the table really hard? Now picture massive stockpiles, massive bins. What happens when that rat hole collapses? Do you want to be around that? Not really. Question.
In some silos, is it true that it could like create some weird suction effect too?
Yes.
Okay.
Yes. So you have major structural issues. So if the rat hole does collapse and the venting is not enough to account for that and let air in, it can actually just collapse like a can being crushed. And I don't know if I have the pictures on this one. I might. Very serious issues. Also, if you have bins with multiple outlets, and one plugs and you're just drawing from one and you draw your silo down on one side, you can also cause dimpling in on that silo because you don't have the hoop stress of the material pushing out against the walls. So if you do have silos and you're looking at multiple outlets, there's correct ways to do it and very incorrect ways to do it. And you have to account for those stresses. Also, whatever you put in first comes out last. It's still sitting there, right? So we call that first in, last out. Philo, some people might say. I heard another speaker say, we call it the fish flow pattern. You heard that one? Fish, F-I-S-H. First in, still here. Still here. It's not going anywhere. Okay. If you introduce a fine powder on top of this, it will flood. It'll flush out just like a liquid. And this sifting segregation. So you have the fines and the coarse. So what happens if that happened in here? What are you going to pull out first? You have this fines and coarse sifting segregation. You're going to pull your fines first, right? And then followed by your coarse material if it can empty out. What's that going to do to your grinding system if it gets just a bunch of fines? It could overload your grinder. Then you get a bunch of coarse. I mean, the fines will overload it, but it's not going to work well. And then you get a bunch of slug of coarse, then it's going to work overtime to try and catch up and maintain that rate. But you know, you don't need this could be a flat bottom bin, like a stockpile. Very shallow, you don't get wear along the walls. So it can be an appropriate flow pattern if the material doesn't degrade over time, if it's not a fine powder. Here's again, another model DEM simulation. So DEM is coming a long ways as computer computational analysis is able to keep up with as long as the computer can calculate it. And so even actually, this is quite a few years old now, but getting a stable rat hole in DEM was a really big deal when it first happened. Sorry, we get excited about that. Don't you? Rat hole on DEM. Woo! So the other flow pattern is mass flow. So you have a smooth, steep hopper wall, and as you discharge, all that material is in motion. Everything is in motion. So you can no longer have a stable rat hole form by definition, right? There's nothing stagnant. Whatever you put in first comes out first. The FIFO flow pattern, first in, first out. If you have fine powders and you introduce it, it has time for material to de-aerate on that top surface as it goes through. Now, if you have fines and coarse in mass flow, what do you think will happen with your fines and your coarse material? What's that? Stay mixed. So it's going to recombine at the outlet. Good job. Give them an extra cookie. Yeah, so it's going to recombine at the outlet, right? Everything's in motion. Sorry, there's no cookies. I got you on that one. So mass flow, that it minimizes the side-to-side sifting segregation. Okay. And much more uniform feed, you're in control of your bulk density. So if you have cohesive material that can segregate and degrade, it's really important. So if we want to achieve mass flow, because this is not going to happen just by accident, you actually have to design for this. Because I can find material that will be in funnel flow with this angle. There's not a magical angle that we'll talk about that. So we have to do the material testing for that. So let's go through these tests. So if you want to design in mass flow, you don't want the material to arch over the outlet. So we need to understand the cohesive strength of the material. We need to understand the frictional nature, because this wall has to be steep enough and smooth enough that particle to actually move along that surface. Okay. We need bulk density, particle density. It's a whole slew of tests that can be done to understand how material is characterized. So there's ways to test that. There's a Janicki shear tester that's been developed. There's a ring shear tester that's been developed. And basically, you guys see snow out here sometimes, I hear? From California, we don't see snow much. We see sand. I live by the beach. It's lovely. So if you take the snow and you just pick it up, there's not much strength to that snow. But if you want to make a snowball, you start to squeeze it, right? Now, because of that consolidating pressure you've applied to that snow, you've changed the cohesive strength of that, cohesive strength of that snow. And if you really want to get a good snowball, what do? You pack it? Is that correct? I mean, you guys live in the snow. You pack it. You're changing the cohesive strength of that snowball. And if you really want to peg somebody, you add rocks, right? Just kidding. I did not say that. Right? So you're changing how strong that material is. So now we need to measure that strength of that material as a function of consolidating pressure. So next time you're in a snowball fight, be like, hold on, I need to add some consolidating pressure to my snowball so I can get you. Don't do that. They'll peg you before you get there. So what we're doing with this tester is creating a consolidated area within this cell, and we're applying a force, the pressure. We're measuring the force required for that material to actually shear and fail across itself. So Jenny said, okay, material will flow out of this outlet without bridging if the stresses on that material are greater than the strength of the material. So like if you have a pen, there's some inherent strength to that pen, and you apply enough stress to it, you're going to break that pen. So Jenny's theory is, okay, if we can figure out how strong the material is, and then how much stress is being applied to that material, we can figure out how big you need the opening to be so the material doesn't bridge. There's science here as I'm trying to get to you guys. And so you can measure it and come up with outlet dimensions to overcome arching. If you do need to design in funnel flow, how big does this opening need to be so the rat hole will continue to not be stable, continue to fall in on itself. Okay, so the strength of the material can change with time at rest. So for this example, we have powder A, B, C for conical. So this outlet dimension here would be like 0.1 feet. So if you didn't want it to bridge, you'd have to design it greater than 0.1 feet as an opening. Now, if you let it sit for 1 day, then it's 0.5 feet. If you let it sit for 3 days, you see stars. And that means gravity alone is not going to allow this material to discharge. It is caked, it's gained so much strength, forget about it, it's not coming out of this bin. How nice is that to know what your scientific data is for this material? And then you can properly design your system. There's a lot to this. We teach 2-day courses on this. You regain it in a quick 20 minutes, 30 minutes. The other half of the equation is wall friction. So as this material moves along that surface, we need to measure the frictional nature of that particle against that surface. And then we come out with a dimension called our wall friction angle. So we come out with phi prime. If you take the tangent of phi prime, that's mu, that's your coefficient of sliding friction. Remember physics class, you have a block on an incline, you have that friction factor. Yeah, sound familiar? There's a lot of those problems that you have to do, right? Okay, so this is that measurement. What is the friction between that particle and that surface? And then there's lookup charts related to that wall friction angle versus your outlet size. What angle do you need to have for mass flow to occur? It's not one magical angle. So here you can see some results looking at, say, carbon steel plate, which is kind of rough, right? Carbon steel. So this is from vertical. Jenny did all his work from vertical. So the smaller the number, the harder, the steeper it is, right? So 8 degrees from vertical. So it's saying if you use carbon steel, then for a 1 foot opening outlet, it needs to be 8 degrees from vertical. Does that seem realistic? Say no. No. Too steep. And then what happens if you let it sit for 3 days in there? It doesn't matter. It's not coming out in mass flow. Now, what if we change a liner to stainless steel with like a 2B finish, like a smoother finish? It's less frictional. It's kind of still fairly frictional. What if we look at like a plastic, a UHMW polyethylene? For this material, it really helps. Right now, 25 degrees from vertical. Okay, we're starting to look at something that can be designed for. Obviously, in mining, you don't always want to go to a plastic, depending on the material. Concentrates might have it. Your ore, probably not so much. All I'm saying here is it's important to test these different liners, different considerations to actually have data to design from. So this what affects flowability. Everything affects flowability. So this was bauxite. I had to go to Jamaica for a site visit. Someone had to do it. And they had bauxite, 22% moisture content. So there's bars underneath. This is a train loadout system. The train dumps the bauxite. It gets stuck on there and it builds up just these straight peaks. To demonstrate it's super cohesive. Well, they would dry it down to 18%, only 4% difference moisture content. And look at the material now. It was like moon dust. That's my foot there. I made a mess. The other guy's like, whoa, dude. Oh, you dusted me out. What a big difference. So if you have data on bauxite at 18%, you're like, hey, this no strength, we're good. But you're actually handling it at 22%, completely different material. You have to consider that and match the process conditions. So you want to test at that range of moisture contents you might be considering. We also have a tester to look at wear. Well, what happens when you do wear a surface? Does it actually become smoother? Because people are like, well, it's going to smooth up. It'll be better after we start running. But for one, if you don't get that initial flow along the wall, it's not going to get any better because it's just stuck to the wall. And two, it could either make a surface rougher, like you see with this carbon steel before and after with bauxite testing, or there's stainless steel after a magnetite concentrate where it just smoothed it up such that you can, it was like a mirror finish. So then the wear test data, that wear values can go into our DEM programs now to estimate wear. So we did this pretty unique design because a lot of times in mining, you have material that is abrasive and also sticky. So in your transfer chute designs, you really have to consider how you're going to handle that. Now you have hoppers, you have feeders that need to go underneath, and it has to make sure that you pull from the entire hopper outlet. One of the biggest things we see go wrong in the mining world is that a hopper or bin is built and then they just have like a gate open in the front and the material just pulls through like either the back or the front. And it's a small little hole, rat hole, versus utilizing the entire hopper. There has to be this interface. And I don't have a lot of time to go into all the details, but it has to increase in capacity from the back to the front so material can feed through the entire hopper outlet. Okay, there has to be these interfaces. There has to be that proper design. It may seem like a very small thing, but you can have what it looks like a great hopper, but you don't have the interface, you're back into your funnel flow regime. Same thing with screw feeders. So what? I've been yapping at you guys. So what, right? Well, let's look at this case study. Anyone look at the have anyone studied the Ravensthorpe? This would be a good one for the classes. Yeah. So Ravensthorpe they started doing some study period in 1999, all the way to scale up in about 2010. And in the study phase, they studied this for 6 hours, or sorry, a long time, 6 hours. Did a lot of work. None of you caught that, by the way, I don't think. Okay, good. 6 years. They did 8 months of continuous piloting. They spent a lot of money on this, really, really top-notch pilot scale. But where was the problem? And turns out the problem ended up being in between each step. So people were looking at their individual phase, but there was a lack of continuous knowledge through the entire phase of the bulk materials handling. So they're looking at their process. Yes, we are able to convert this material into the precious metal that we want to have. But looking at how are you going to actually handle it? And so there was no focus on the flow through the entire system. The laterite ores are known to be sticky. That front end comminution and beneficiation circuit was a generic design. It was that copy and paste generic design. It was not accounted for the sticky material. And as a result, it only operated at 35% of the nameplate ore throughput. 35%. Is that good? What percent do you want to be at? 100. And then they want you to go higher. So what happened? We believe, and the studies have concluded, it was a very cognitive bias. Like everyone gets very focused on the process. Here's your key process. I mean, people like Star Wars are all focused on the key process. Anyone see this little star? That's the bulk solids handling component. Nobody's looking at that. It was well, it wasn't even after that. They just didn't even pay attention to that part in this case. And I was presenting this at an engineering firm. And then one of the ladies in there, she's like, I was on that project and you were absolutely correct. I got, glad she said I was correct. But she's like, it was terrible. We worked so hard on this project and to have it not work is just devastating. So when you do get on a project team and you get involved in these kind of processes, make sure that everything is being accounted for, not just your little section. So we do that by a technique called capability mapping. What do you have? You have your HSC, you have your process, you have your engineering firms, you have all these components. Make sure there is somebody focused on bulk solids flow. So they made a bunch of changes, tried to get this to work. These are articles that were published. And the changes we have made have been far-reaching but fairly obvious. In hindsight, we quickly realized that the hydrometallurgical plant had been very well designed. It was one of the highest quality. All the problems were at the front end, particularly in the crushing and materials handling components. Okay. So important. The impact of that, I mean, they had to just tear out equipment. Oh, they spent over $2.2 billion in this. Over 1,000 contractors. So make sure we know what's happening, understand the material flow, talk to your team. There's data. I just want you guys to understand. I know you're early on in your careers, you're still in school, but this is really, really important that somebody has to be focused on this. Does that make sense? The science is there. Any questions? Yes, in the middle.
Should that biomass be in like flow? Is there anything else that you found that is really resistant to flow and always has a problem?
Yeah, good question. What the question is, are there other materials that always seem to cause problems? In the mining world, the higher the clay content of your ore, more likelihood that you're gonna have problems. Pay attention to that. As you move throughout your mine, you may come to pockets with higher ore or higher clay content in your ore. Because clay is just sticky. Doesn't want to move. When I was in Australia, the operators say, yeah, I just pick up that ore, throw it against the wall. If it sticks, I know it's a bad day. If it doesn't stick, it's a good day. So it's putting science to that movement. Biomass is definitely one that humbles you, and you really need to know what you're doing. The scale up of biomass is very tricky because you may have figured out how to handle it in a small scale because there's not great pressures on it. And then they go and scale up to these big processes, and all of a sudden they just can't get the material out. Good question. In the back.
Material flow here, you have a funnel for a convex.
Okay, yeah, good question.
Kind of how it naturally seems to orient itself.
So there's a lot of the question is there a different like hopper configuration,
Right.
convex that can make it flow?
Curved instead of just having to-
Yeah, so at some point you have to look at your feeder. So gosh, there's lots I could talk to you about this, but a conical hopper is the most restrictive way you can handle a material. It's the most unforgiving way to handle it. If you go to now a planar hopper, because if you think of a conical like this, and all of us like trying to rush out of this one door, it doesn't go well, we interlock, right? We're all the particles are trying to move down to that. If you go through a planar hopper and basically open up this side of the wall, we can all exit quite easily. And because you're not coming through, it's much more of a forgiving design. If you have biomass, there's ways we do converging, diverging bins, it's called. So you might converge in one direction, actually diverge in the other direction. So you're not applying too much pressure to that material. Eventually, you do have to get it down to a size, usually for a typical feeder. You have to consider the feeder you're going to use. There's some live bottom configurations where you have feeders or multiple screws where you're not converging it. It's very expensive, but sometimes it's justified. And this is how you can have the data to prove that you need to do that. So there's a lot of different configurations that are out there. Good question. Yeah. Your turn this time, not behind you.
Okay, thanks. You know, in the underground non-metal mining, particularly when we look at ore passes and drop, they're some of the most dangerous elements in an underground mine. We have fatalities every year that occur because in some cases, the superior, we have 5 people killed in a single incident. But one of the things that comes up when we look at this is bridging and blowouts and hangers. Is there are effective ways to mitigate it, particularly in methods like caving and some of the stuff. They're right now the current state of the art is to put an explosive someplace up the chute around the head or around the brow, or you start dumping water in the top, which actually creates increased hazards.
Yeah.
So you guys deal with that stuff?
Yeah, so the question is underground mining. It is really challenging when the ore passes do get plugged. And there's some limited ways to handle that. The work that we've done with the ore passes is characterizing that to see maybe what the worst condition is, and then how maybe the shape of the ore pass can diverge it at all. If you can, it depends on where it's going down. If it's going back down into big slotted, then once it does bridge or arch up there, it's a tough one because it's already in place. Yeah, explosive sometimes has to be used. The water, I can see what they're doing. They're trying to reduce that cohesive strength, but then you have to deal with the water, and then it can just all slug out. So
But that's always a problem. NIOSH is looking at this.
yeah.
For probably no more than 20 years.
Mm.
to come up with a viable solution.
Yeah.
It's kind of interesting.
And part of it is we look at the blasting, are they over blasting, are they under blasting? Your interlocking of the particle sizes versus the fines, because if you start over blast, you get a lot of fines. It is complicated. Yes.
Ravensthorpe is very, very good example. 15 years ago, worked with some displaced PhD engineers. And the flow sheet with this additional common usage, so that would have been the first, because probably the last thing you want to do is additional common usage of the ladder.
Mhm.
So that's it. Does Genesee ever interface or collaborate with combination equipment manufacturers? Miners, because oftentimes it's might be like a sizer or laterite.
Mhm.
It's more forbidden and not related. You work separately.
Well, we try and work with, so the question is, on these projects, do we work with we'd love to try and work with equipment vendors to get the right sizing. We try and encourage, a lot of times what happens with these equipment vendors is that they're given this thing, say, hey, we need a price right now.
Right.
And they don't have the data of what this material really is like. If they're lucky, they get a particle size distribution. If they're lucky, they try and maybe an angle repose, maybe bulk density, but that really doesn't tell you how it's going to flow. So our encouragement to them is you have to push back and get some kind of flow data on that. We try and get involved early on with engineering firms we want to be the voice of the dirt, the powder of the bulk material. Like, be the voice. Hey, if you're going to do this to me, this is what I'm going to do to you. I'm going to get stuck if you try and handle this material this way. So yeah, I love working with them early on, and the equipment vendors, I really get it, especially people that have been burned. They know when they're going to get burned and they get the right people involved. Unfortunately, my encouragement to you is don't get burned. Just get the right people early on.
Well, it strikes me that a role that Jenny plays is formulating and understanding the characteristics of the materials, which would then lead to the correct selection of
Yeah,
equipment for
absolutely.
that purpose, right?
Right. And everybody looks better, and it makes so much sense. And then relatively speaking to the entire project cost of billions of dollars, sometimes you get pushback if they don't want to spend $20,000, $30,000, $50,000 in testing. You're like, oh my gosh, but you're buying these $1 million pieces of equipment, yet you don't have any basis of design for that. And you may be the one trying to make this decision, not having any basis of design. You know, speak up. Yes.
So have you tried the dynamic nozzle just of feeders that can change shape and inclination just like the fighter jet nozzle?
No.
Have you tried that?
Like having the hopper change shape?
Or like
No.
the outfit? Because I believe in mining, since we mine ore from different locations in the mine, then for sure the characteristics will be changing. So I need something like this. Have you considered that?
Yes, especially like with the transfer chute design, getting a transfer chute that can kind of modulate, make it a smart transfer chute. And we just won I guess we were one of the last contenders for a R&D 100 award for smart transfer chute design. It's like, how can you get an input of the moisture content or some change that we know will affect how it's going to flow through your transfer chute and have the transfer chute adjust for that. With hoppers, going down to that conical hopper is just not a very robust design. So I'd probably say we want to definitely usually go into a planar design. And there's ways to make that very robust to handle most of the issues. But sometimes we have to tell a client, if you get this slug of really high clay content fine material, you actually have to divert it off until you can get some more coarse competent material and then blend it before it goes into your process system. So you have to either change the equipment or change the material to get it to flow. Good ideas. Yeah. So how can you adjust that? How can you use your equipment properly? Good question. What else? Right in the middle. You middle. Corey scratched his head.
No question.
Go ahead.
Oh, okay. You have to deal a lot with like interacts, like the chemical problems as well. Like if it
Yes.
heats up being tumbled around or cools down.
Yep.
Something like that. That
Yeah.
changes a little bit.
Yeah, so material can definitely change with heat, so it can soften. We had a project, so at a power plant, so the ash that comes out from the burners gets collected. It's gonna be fly ash, sometimes bottom ash, and it's super hot. But when it's dry, it's just like free flowing sand, about the easiest thing to handle. So they designed these little conical hoppers to collect this fly ash. But the problem was at that temperature, if that fly ash stopped moving, it actually sintered together. And from day one, that thing did not work. So sad. So we actually tested the material. We have a furnace that goes up to 1000 C and these things glowing, and we're measuring the cohesive strength. And by golly, we tested at those conditions and saw that, yeah, it definitely sinters and cakes together. That's exactly your problem. Here's how the wall friction angles changes. And so we gave them a retrofit solution. Had they done that testing ahead of time at that temperature, they would have saw there's no way that design they put in would have worked. So things that soften hot cocoa powder, conveying that as it heats up, it's going to want to stick to the elbows, right? Because it's supposed to melt. Has fats in it. Food is very fun, besides the fact that I like food. But it does change with temperature. It changes with moisture, right? Plastic pellets, if you convey it and they warm up, they actually like string out and they have these like long strings. That's not very fun to handle. I know we're reaching time. Any other questions though? And I'm going to be here. I have business cards. If you can email me further questions. Make sure you take a model. I flew with them out here. Don't want to fly out with them.
Thank you.
Just want to say, undergraduates, thank you so much for coming. We do this every Thursday. You guys are more than welcome to come every week.